Okay. Hello, everybody. First greetings from me to entire audience who listen us. So we will start with the today's section 11A, Robotics and Automation. I will first introduce myself. I am Marjan Golob, Associate Professor at the Faculty of Electrical Engineering, Computer Science and Informatics at University of Maribor in Slovenia. My teaching and research interests are mostly focused on industrial automation, distributed control systems, machine learning, and probably intelligent control. Today in this section, we will follow the presentations of the 6 interesting contributions. All speakers will have approximately 15 minutes for the presentation and together with discussion. So please be careful about this time. So I think we can start with the first presentation. The first presentation, the first paper with the title "An Optimal Control Method for Autonomous Surface Vessels for Environment Monitoring and Cargo Transportation Applications," will be presented by presenter Heigo Molder. Presenter comes from Estonia. So welcome. The floor is yours. You can start with your presentation.
Yes, thanks. Right now he can't allowed to share my screen because some other
yes,
participants.
Okay. I will share this. Yes, just a minute.
Now it's okay.
Okay.
Just a second. I hope that everybody sees now.
Yes, we see it.
Hello, so my name is Heigo Molder. I'm from Tallinna Technical University in Estonia, the Department of Power Engineering and Mechatronics. So me and my colleague have write an article which name is Optimal Control Method for Autonomous Surface Vessel for Environment Monitoring and Cargo Transportation Application. So we have, me and my colleague have a deal several years already for autonomous surface vessel, which name we call it MIMO. And actually we are not working out autonomous robotic boat, but we're trying to build up the control system or the brain for this autonomous surface vessel. So the prototype, we have a prototype, and the prototype is around 2.5 meter long and 1.1 meter wide, and he has it's a catamaran type boat, and he has 2 motor. Both of them is 1.5 kilovolts. This prototype boat is able to carry around 100 kilograms. The maximum speed is not very high, 11 kilometers per hour, and it's working. He's using lithium ferrum batteries, 2 batteries, and the operating range is around 100 kilometers. So where we can use this kind of boat, there is possible to use different application. One application can be to carry the package one island to the other, because in Estonia and also in Nordic countries we have a lot of islands. So and how it works, you just need to add a mobile phone. You can put some kind of coordinates in your map, and the boat is trying to go. And when he meets some kind of objects, then he how to say knows how to turn around this object. So Of course, it's not perfect yet. It has some problems. And one problem what we're looking in this article is that in the beginning we have a lot of problem for overshooting the trajectory, and we're trying to find different mathematical application for doing this robotic boat more stability. So in this article also we're looking some Simulink and MATLAB software calculations. So yeah, but this boat is also possible to use. There is possible to put different sensors, sonars. We can look down to the water, and yeah, it's possible to use it different application. Also clean to the water and take some kind of environment probes. The boat is built up quite a modular way. Because it is catamaran type, we can change this swimming button distance. So we can get a little bit bigger platform if you want. All the smartness or this how to say artificial intelligence is sitting in this black box, and it is built up this way that we just can connect the cables out. And then we can put this smart box, whatever swimming platform. Also, we need to put some kind of sensors around the boat, and we have already some kind of situation awareness. So also the boat knows traffic rules, call regulations. He has also autonomous charging dock, also 4G communication, and 432 megahertz to use it the manual way. So yeah, but if we're looking different research articles in this area, then we can see that we can find a lot of different articles which touching this how to say flying drones, but much lesser the articles which is dealing with this surface vessels. So yeah, we're trying to a little bit fix this. So we also try to do some kind of science in this topic. So yeah, but going to the article, as I mentioned, we have some kind of problems in the beginning to get the stabily trajectory. So we're starting to deal with this topic. So we have in the beginning we need to take two different coordinate system. If this is global coordinate system, and this is how to say local coordinate system, or the center of the mass coordinate system. And if you want to calculate, example, heating angle, boat heating angle, one coordinate system to the other, then we can use this simple equation. So as I mentioned, this is a catamaran type robotic boat. There is a pushing force. The symbol is T1 for this. And there is also taking into account way moment force, which is pushing the boat for how to say diagonal way. Or also the U is the speed of the to this way, and the V is for the how to say diagonal way. Yeah. So how to calculate out in the beginning, we're looking both dynamical model. If you want to get the heat angle, then we need to put, we can use this kind of formulas. We can put desired end coordinate parameter inside, and then we can calculate out the heat angle corner, what it should be. So yeah, this and in a kinematic system, there we're taking into account also this how to say this speed in one way and the other way, and also the rotating speed, and then we can calculate out this Y moment, parameters. Also, we're doing some kind of simplification for these calculations without taking into account right now wind. Also, wave we have neglected for this modulating part, but real life, this is, of course, we need to taking this account also. And also what we have done is that we take into account right now this hydrodynamical damping as a diagonal wave. But this hydrodynamical damping actually depending on the boat, how to say, mass, because when the boat is going more in the water, then the hydrodynamic damping is growing. So these are equations for a dynamical model. If we want to calculate out speed or rotating speed, then we need to take into account this inertial mass, which is taking right now 200 kilograms for this boat. And also we need to take into account this damping factors, this D11 and D22. And also we need to take into account the pushing force, which is D1, and also wave moment, or the force which is trying to rotate the boat. So yeah, and we need to how to say, find in the mass of the center of the mass, this heating angle. We need to take the integral of this coordinates. So next, we have find some good articles that if the stabilization is not very high, it's around 5%, or the overshooting is around 5%, then we can use this kind of formula to calculating out this Y moment force. So we can use their two constant, which makes our calculation a little bit more simple. And we find this constant for these articles, these two articles. If you want to read this more detail, then these are mentioned also in articles. But one constant what we're using there is T11, and this taking into account this desired transmission time. So and the other constant what we're using is constant K, and this taking to there is some other parameters like N and mass, and this N depending on the desired transmission time heading angle, and estimated transmission time secondary delivery of heading angle. And also we take into account this inertial mass. So and also this in simulations we put it parameters, this D desired angle, it takes around 10 seconds. So we have built it up what to say, scheme for MATLAB. And there we have a block diagram, like where we have a force control, which is pushing the boat. There we have a dynamical block, and there we have a kinematic block, and there we can get output coordinates. And also there comes feedback for this switch relay. And in switch relay, we can in the end, when the boat has going to the final point and starting to rotating in the end point, then we can just switch the constant Y control moment on, and this switch then we can use. But other way, the control moment is calculated using this formula what I mentioned before. So yeah, in this MATLAB we can put desired coordinate inside, and we're looking right now two different cases. So one case is the x coordinate is 90 meters and y is 50 meters, and the second target we have both 50 meters. So and the pushing force we have put it 50 newtons right now in the simulations, and also the moment which is trying to rotate the boat in the beginning, in the end point we just within 3 Newton meter. So and what we have get it for this Simulink on MATLAB, we have get it a graph where we can see this moment or the force which is trying to rotate the boat, and when the boat is are in the end point, then I don't know, so yeah, the laser point is jumping just, but the end point where the boat is trying to rotate for the end point, then we just switching the moment for a constant value, and then it's 3 Newton per meter. Yeah. So and this is the head angle, how this changed in the test, and yeah. So next slide. This is the other case where we have endpoint is 50 meters in x direction and y direction also. So and you can see that it's quite stability, and when in the endpoint it's starting to rotate in the 1 point. So we can look this both case in compare each other, and we can see that it's working quite well. So and actually we have dealt this topic quite long already. We have write one article in Hungary 2019, and then there we was looking proportional control method, and then we don't get it really stability output. But last year we also write one article in Estonia conference, Baltic Electronic Conference. There we trying to use it neural network predictive control methods, and there we get already quite good stability. But in this article we have using this proportional control method or nonlinear control method, and there you can see that it's giving us much better results. But if you're using this neural network predictive control method, it's how to say, the point was there is that you need lot of statistics. But if you have a lot of statistics, maybe then this neural network method is also okay, because then it's going much more stability. But this method what we have used right now gives also for us quite good results. So conclusions. We have how to say, find a quite good result for our robotic boat. It's working quite smoothly and fast, getting quite fast stabilization. Yeah, we have get the quite practical results also. So yeah, I don't know how much time I have.
Yes, the time is gone.
Okay, then I don't show the video anymore. So, but that's it for my side. If you have some questions, then.
Okay, thank you very much for your presentation. We have time just for maybe one short question. Is anybody of you want to ask something? No. If not, then maybe I will ask you, did you also do the validation of your model with this controller with real data sets from your boat?
Yes, actually, we have this last year's article, what I have been mentioned. This is also we have tested for real time or real life data. Yeah, but this article, what I presented right now, this is we haven't put this algorithm in the real boat. So yeah, maybe this can be our next article.
Okay, thank you, Mr. Mulder, for your presentation. We will continue with the next paper. Next paper with title Combined Harvester Cooling Water Temperature Prediction based on CDAE-LSTM-hybrid model. This paper will be presented by Mr. Yining Fu. Please, Mr. Yining Fu, you can start with presentation.
Nice to meet you.
Okay, thank you.
Well, thank you, Professor. My name is Yining Fu. I'm from China Agricultural University. It is my honor to be here to join this forum. My topic of my presentation is combined harvester cooling water temperature prediction based on convolution denoising autoencoder and long-short time memory hybrid model. My presentation will include these parts. First, I will give some background information about this research, some introduction and analysis of cooling water temperature prediction. Then we will introduce the main work we had done and give the conclusion and innovations for the future work. So in recent years, information collection technology have been widely used in agriculture. Informatization and automatic control make work more convenient, but it also brings some problems, like low data utilization, lack of bias for decision making, and unbalanced detection technology. So we want to achieve a variable for this problem. Therefore, the study on data analysis is pay more and more attention, especially in history. Machine learning to deal with this. It must be guaranteed 3 parts. The method cannot affect the whole system while deal with the agricultural problem well, and it can process large amount of inspected data and aiming at output a reasonable decision. In our paper, we choose cooling water temperature as this target. So there are 2 questions: why we choose cooling water temperature and what condition we meet. Cooling water temperature can reflect the change of machine's power consumption and even overload. So we choose this as our predict term. Then the condition for the working condition, field equipment working condition is harsh. We want to use machine learning. Its effects are greatly influenced by the original data. And in earlier research, omission of time series data is very common. So the next question is how to make a reasonable use of collection data to predict the temperature. So the main work, back to the research, the main work we have done as the 3 parts. We created a hybrid model to predict the cooling water temperature and use convolution denoising autoencoder to denoise the input. And then we use the statistical method to analyze our prediction result. First, we do is analyze the combined harvester operation parameters, calculate the correlation of parameters. And after we analyze the future of these parameters, we found the original data has a continuously sequencing and with noise inside. So our prediction model needs anti-noise ability and good time sequences processing capability. We choose the core between 0.02 and 0.052 to predict our cooling water temperature because we need to guarantee its individual. So as for the analysis of time series, we use long-short time memory to deal with this problem. Long-short time memory can process continuously time sequence and predict cooling water for a short period in the future. But we also find the long-short time memories have weak point, such as future instruction is not good enough and predict hysteresis. So we want to combine the convolution neural network with it and to aim to get a hybrid model to grave this problem. For history data itself, we use autoencoder to reduce noises. The original noisy data is caused by sensors or people operation and environment. So we need to guarantee the noise reductions model can clean this noise. The noise reduction model's output should be in the same format as the input model and get its output for our hybrid model to predict cooling water temperature. However, same as the other autoencoder, it also have great resource consumption. Therefore, the field test we established to test the model's effect. New history data collection was used to adjust the model, and the figure showed the overall structure of it. First, we collect the census data from the test in China. Then we decided an input format to train our model. Before transformer learning, we do the pre-training and noise processing. At last, we focus on the model evaluation. This picture show the field test in Shandong province 2019. And the left show the collection box and part of real data. Sensors and other equipment are introduced in our test session of our article. I'd like to tell how we pre-training before adjust the whole model. After obtaining enough experimental data, we use ground research and the random research to adjust the hyperparameters. This is the range of the filters of a convolution neural network and the range of the other parameters like kernel size. For the self-encoder can comprise and construct a singular, and the noise cancelling self-encoder is unbiased for autoencoder by any noise and learn how to clean it. The figure shows the structure of it. When we adjust the convolution denoising autoencoder, we just need to adjust the single layers or the hyperparameters in this structure. As for prediction hybrid model, it includes feature extraction part and the prediction part. We know the convolution neural network's input is not supposed time sequences directly, so the role of the convolution neural network is just to extraction features, and is output as the input for long-short time memory. The role of long-short time memory is to predict the cooling water temperature. We need to reshape the data into sensors so long-short time memory can do this work. As seen in this picture, we choose the correlation parameters, just like engine speed, routing speed, and others into the long-short time data sample, and choose many-to-many long-short time memory to create a short-time cooling water temperature. The convolutional denoising autoencoders parameters table obtained after revise as shown in this. We can see the results of the structure, adjustment of some parameters after pre-training. Hybrid model did the same parameters migration. So we can say we use long-short time memory to replace the one replace the 1D convolutional layers in this place, and it is also can cut off the computation expensive. In order to verify the stability and its establish and the effectiveness of the prediction method, experimental result analysis is very important for us. We hope to expect the source of the data is true and reliable, and the treatment is reasonable. The accuracy of prediction meets our requirement. So we make some equipment and choose some sensors to the test in the field and of online pre-training. In the end, we use statistical analysis and imagine trend analysis to achieve this goal. We evaluate a model by using variety of statistical, such as mean absolute error, root mean square error, and R-square. Picture prediction can also show the fitting degree of a hybrid model and the control model. In the left picture, we can show the original long-time memories is weaker than the hybrid model. And this picture is before convolution neural before reduce the noisy. And we use the motivation rate to define the details of it, and we will show in the later. For the noise reduction effect of convolution denoising autoencoder, the output is marked as a predict by an analyze a single input. So if we input, if the input is speed and the output is also speed, this picture can show the reduction effect is obviously after using the convolution denoising autoencoder. After reduced noise, we compare the original long-time memory and long-time memory model and with the convolution neural network and hybrid model. We can see the degree of the fittings is better than the original model, and the loss chance is faster convergence. But there is still some problems. Both model has a peak prediction work not well. Therefore, the future research we should care about this because it is important for our control system to determine threshold. This is very important. We'll also test the BP network and use statistical to guarantee the specific efficiency. Hybrid models statistical plays well. The root means absolute error and the mean absolute error is 0.0817 and 0.0989. The R-square is 0.9785. As we show in the table, compare with the long-time memory model, the promotion is nearly 13%. So in conclusion, we use the convolution denoising autoencoder to create problem in noisy data and outlier our proposal hybrid model to solution to it. Then we use the hybrid model to predict the cooling water temperature. So this improves the ability of machine learning, which can be used to solving the agricultural problem and possess a large amount of agricultural data. There is much work remains to be carried on, such as although the ability to pretend the train seems well, but in in the outliers seems not effect as we expect. This makes it difficult to take a model to carry on and without solution it. If we want to make the 4 diagonals research now, we should solve this problem. So we hope to make more efforts in the past and adjust our model in the future. Thank you. If you have any question.
Thank you very much for your presentation. Please, questions from the audience. Yes, any questions? No, there is no questions. I don't see also in the chat, there is no questions. Okay, maybe I will ask you something. So this convolution neural network is of course very powerful tool for such applications for modeling and prediction of the process variables and so on. But you need a hardware. Now, hardware is very important. On which hardware you run this your hybrid model and convolutional neural network? Which hardware do you use?
Yes, the heart of our hybrid model is long-term time memory, because we need to deal with the sensors time series data. All of our collection data is collection to time. So if we don't deal the time sequences, we couldn't never to do the other research, just like how to control the machine to deal the other agricultural problem. So this is important, and others just like convolution, denoising, autoequator is just to help the long-term time memory to do the prediction.
Okay, thank you very much, Mr. Yining, for your presentation.
Thank you, Professor.
Now we will continue with the next paper. The next presenter is Mr. Fatih Adiguzel from Turkey. He will present a paper, Robust Discrete-Time Nonlinear Attitude Stabilization of a Quadrotor UAV subject to time varying disturbances. Mr. Fatih, you can start with your presentation. You are mute, Mr. Fatih.
Yes.
Yes, now we hear you.
Sorry. Yes. One problem I can.
You must share the screen and then presentation.
Yes, I can. A problem. I solve it quickly. Please, the problem caused by flash bellek, flash
memory.
Okay, memory bellek.
Maybe we can go with next presentation.
Just a minute, maybe.
Yes, okay.
Okay, we can continue with next presentation, and maybe later you will present your.
No, I can start, Professor.
Aha, okay.
Okay.
Okay, then you start, please.
Very sorry. Very sorry. Thank you, Professor. Hello to everybody. My name is Fatih Adiguzel. Co-author is Tarık Veli Mumcu. Both authors are a member of the Istanbul University Cerrahpaşa Electric and Electronics Engineering Faculty. Our paper titled Discrete-Time, Robust Discrete-Time Nonlinear Attitude Stabilization of a Quadrotor UAV subject to time-varying disturbances. The presentation content can be given as introduction to UAV system, especially Quadrotor. What important does UAV systems, dynamical model and problem definition in this paper, and disturbance observer design for attenuation, constant and bounded time varying disturbances. But particularly it used for problem caused by time varying disturbances. And then controller design. This section include discrete time input output feedback translation controller with a digital filter or PI-like controller, which solves many difficult problems. Such as parametric uncertainties, discretization errors, and the controller structure employs the estimation disturbance values. Simulation results and conclusions. Recently, UAV systems are paid attention by researcher and academic area and industrial area due to using military, transportation, and environment areas. In the system, the main control problems can be told as position control and stabilization or attitude control at the certain height. For these purposes, many nonlinear control methods can be applied to this system, backstepping, sliding mode, input-output feedback organization. Bytes, as we know that these controllers are designed in the continuous time, but it applied to system in the discrete time. Thus, this paper with this motivation is deal with stabilization or attitude control in the discrete time, tracking lots of different problems into account. The general Quadrotor UAV system used in this paper is presented in this figure. Here, B body frame, E earth frame, phi, PC, phi, and theta roll picked, and yaw angles, Euler angles, X, Y, and Z are Quadrotor gravity origins. F1, F2, F3, F4 stand for the thrust force by the rotors, which are static. And translational and rotational dynamic using a Lagrange approach are given as these equations. In these equations, U1 and U4, this U3, U1, such as, are called controller input signal, and D2, D3, D4 with a bar syntax are external disturbance signals, which are time varying or constant external signal, and all other parameters and details of the dynamics are given in paper. In this paper, Quadrotor UAV discretization equation are obtained with forward Euler approximation, which can which are well known in the literature and using deeply. Or name linear extrapolation methods. The discretization methods are given in detail in the paper, and defining these sets for compact presentation, the controller structure, and this set. The transformed continuous time attitude system dynamics are given by these equations in the compact and where f and g function are presented clearly in the appendix of the paper, and y is the output which wants to be controlled, and due to the nature of quadrature system, it can contains the extremely high nonlinearity system parameter participation, and it's copied with different types external disturbance, time varying, constant, and discretization problems since performing digital platform. And this meaning of setlist tracking for a quadrature system is provided with can provided with input-output realization control together with pre-controller or discrete-time filter, digital filter. Firstly, I give discrete time disturbance observer design. The theorem considers discretized attitude dynamics, estimation dynamics of the external disturbance asymptotically stable under the designed discrete time nonlinear disturbance observer structure given by this, if satisfying this condition. Where Z, D, I hat, and B, beta, and L estimation of external disturbance, augmented state variable Z, and estimation of the external disturbance D, and auxiliary nonlinear function depends on state variables beta, and L2E is a nonlinear disturbance observer design parameters for imported as. Please see for proof of theorem and the paper to paper, and it is important that note that with the assumption of changing much slower quadrature dynamics than time varying disturbances, if observer design L2E is designed beta is designed with an suitable assignment which remaining within the unit circle, which is means jury stability test, and then the observer error dynamics asymptotically fast converges to 0, which is the final for disturbance observer slide. And controller designer, a discrete time nonlinear input-output feedback minimization control is presented for stabilization for attitude control. After the controller design, the controller, the quadrature attitude subsystem transformed into a linear system with cancellation highly nonlinearity is effect. However, and the linearized attitude system is affected by parametric uncertainties, external disturbances, especially constant and time varying discretization error due to digital platform application. In order to attenuate the mentioned errors, digital like filter can be designed, which is block pre-controller, I and I disturbance, I and I linearization controller. but moreover, being more robustness against bounded time varying disturbances for system performance is performed by a nonlinear disturbance observer, which is which given last slides. This block and detailed design steps are removed in the presentation slide due to time limit. However, all steps are presented in the detail in the paper. But I can I can give a short of the controller design. The input-output realization controller can be designed these equations, and after this controller, the system linear closed-loop input-output dynamics can be given as this equations, where row 1, row 2, and row 3 are design parameters. And in order to apply to input and output feedback realization controller to a system, some preconditions must be emphasized, such as relative degree, zero dynamics, and minimum phase specifications. All the whole specification are satisfied, and these are shown in this paper in detail. And simulations, in order to examine the effectiveness and robustness of the design controller structure for stabilization problem on the nonlinear full attitude full uncertain quadrature behavior, several numerical simulations are carried out in MATLAB with a fixed sample time 1 microsecond, and the solver is set as 1 microsecond. And the saturated value is 24 Newton, and all parameters of the quadrature are considered as uncertain, and the controller is known 80% of the actual values of the all parameters. And all design parameters these design parameters can be given these values. For example, linear model design, this polynomial, and the numerator of the pre-controller or PI-like controller its design can be this polynomial. And nonlinear disturbance observer design gain is selected this value. These parameter values are designed by trial and error approach, and this results for phi x1, x2, d2, d hat estimation of external disturbances, no disturbances, constant disturbances, and time varying disturbances, A, B, and C part in the interval time 0, 5, 5, 8, 8, and 20. And final column U2, the control input signal. This figure are this figure are given different three different scenarios: disturbance observer within the control disturbance observer within the control structure, and control structure without a disturbance observer, and the assumption in which the controller estimates the disturbance signal exactly can be given as black, blue, and red respectively. Note that constant parameter perturbation or disturbances occur in the steady state error in the system output. And the pre-filter is active with the simulation runtime. Thus, the effect of the parameter uncertainty is not observed in the simulation result A part, But however, it can be understood from the simulation result B part, which is affected, completely rejected under the constant disturbances. When applied the constant disturbances to each Euler angles at the 5th second, the disturbance influences have been separated without disturbance estimation. Without the nonlinear disturbance observer, this system is already asymptotic stable and performs the robust behavior, A part and B part. On the other hand, when time varying arbitrary disturbance sinusoidal-like signal at 8 second is presented to system, and the result can this result don't execute the same performance anymore. And it can be clearly show that capability of the attenuating the external time varying disturbance of the proposed controller with a nonlinear disturbance observer has a rate of roughly 4 times black and blue line. And by size, there are almost no difference between the controller, which is to utilize the estimate disturbance signal, and using the estimation in which the controller estimated previously the disturbance signal in the controller. This blue and red line. And this performance of the nonlinear disturbance, this result illustrate the superior performance of the nonlinear disturbance observer, which can be seen this simulation results. And conclusions. This discrete time robust controller with an nonlinear disturbance observer is proposed for attitude stabilization of nonlinear Quadrotor behavior, and the main conclusion are summarized as follows. In the discrete time setting, attitude stabilization of a Quadrotor, nonlinear Quadrotor, this is performed considering system internal and external and uncertainty and linearization errors. And attitude performance is supported with an nonlinear disturbance observer by employing this stability analyzed in the discrete time, and closed loop system dynamics is evaluated in the sense of Jury stability test. Okay.
Okay.
The final is a fast presentation.
Thank you. Thank you, Mr. Fatih, for your presentation. Please give the questions from the audience. Will anybody ask something? If no, okay, then my question is, okay, you present simulation results. These simulation results are very promising in terms of possible applications in the real experiments. So my question is, what problems do you expect when you do the real experiments on a real quadrocopter? And how will be what do you think about convergence of the nonlinear observer? How this convergence will be on the real system? Convergence of the parameters.
Yes, it is a problem in case the perform the test on the actual Quadrotor system. The main problem is allocation a digital sensor system with noises and disturbance signals, but disturbance signals on open door area randomly, maybe. And the other problems is controller tuning parameter. I know that. And input-output linearization control is sensitive to parameter, constant parameter, system parameters. And the works includes only attitude control, but the system has position control, position distinct. Maybe a lot of problems arise in the test system, but the simulation results can actually perform it in detail and simulation simulating in MATLAB and file coding.
Okay, thank you. Thank you for your answer.
Thank you very much.
Okay, next presentation will present Miss Angela Georgievich. Hello.
Hello.
And the title of the presentation is Model Predictive Control of Nonlinear Multi-Input, Multi-Output System based on Adaptive Orthogonal Polynomial Networks. Please, Miss Angela, you can take the floor for presentation.
Okay, thank you. Today I will, hello everyone, my name is Angela Georgievich and I will present paper Model Predictive Control of Nonlinear Multiple Input, Multiple Output Systems based on Adaptive Orthogonal Polynomial Network on behalf of the team that did this research, Professor Marko Milojković, Stanislav Perić, Professor Stanislav Perić, Professor Miroslav Milovanović, Professor Zoran Perić, and Professor Nikola Danković, and me, of course. So we proposed a new design of model predictive control, which is based on specific models in the form of adaptive orthogonal polynomial networks. And these networks were built around specially tailored bases of generalized orthogonal functions. The main advantage of these networks is that have when compared to some classical neural networks used for MPC, is that they have a single layer structure and smaller number of parameters than classical neural networks, which leads to lower complexity and shorter calculation time. Adaptability of our model is achieved by incorporating additional variable factors inside orthogonal bases. And we tested the proposed control strategy in control of twin rotor aerodynamic system. So generally, model predictive control is advanced feedback control method, which proved to handle multiple input, multiple output systems exceptionally well. And it has ability to anticipate future events and take adequate control actions to ensure good tracking performance, closed loop stability, and robustness. The main drawback is that MPC requires use of strong processors because it requires a great number of calculations in real time. So that's why it was firstly used in for some slower processes in petrochemical industry, for example. But the evolution of processors with large memory enabled the application of MPC not only in process industry but also for fast systems such as aerodynamic systems. The proposed MPC structure is presented on the slide. So our MPC controller consists of orthogonal polynomial model, that's the adaptive orthogonal polynomial network, and optimization block. So first step was determining the model of the system by using this orthogonal polynomial model. When the training was over, this model actually is used to predict some potential future values of the system output based on currently applied tentative control input, previous values of actually used control inputs, as well as previous planned outputs. These predicted values are then used by optimization block together with the desired response in order to determine the optimal control signal. This is done by minimizing objective function. We use the objective function presented here on the slide. So it is actually a weighted squared sum of the predicted errors and control signal increments. So it emphasizes not only small tracking error, but also smooth control. And when the optimal value of the control signal is determined, it is then applied to the system, and this process is repeated for every sample. Important thing that I didn't mention is that our orthogonal adaptability of our orthogonal polynomial model is achieved by using this additional variable factor delta. The system we used is laboratory laboratory twin rotor aerodynamic system, or TRAS, which imitates simplified controller. It has 2 degrees of freedom, which are represented by 2 rotors driven by DC motors. The goal was to stabilize the beam carrying the rotors in an arbitrary position, or to make it track some desired trajectory. It is important to state that this system is multiple input, multiple output system, and it has high order nonlinear dynamics present along with the cross couplings. It's also prone to variations, external disturbances, unwanted induced vibrations, etc. So it is a challenging task to design an adequate control algorithm for this system. To determine the model of the system, we used adaptive model based on orthogonal. We used adaptive orthogonal polynomial network, and other authors of this paper have previously designed some new forms of orthogonal polynomials. Here we used generalized Legendre polynomials as the basis, and these quasi-orthogonal functions were the basis for designing this model in the form of adaptive orthogonal polynomial networks. This network actually generates a function which is actually a sum of weighted Legendre polynomials, and it is capable of approximating an arbitrary function. The main advantage of these generalized Legendre polynomials lies in this adaptive factor delta. This adaptive factor is actually used to model the operating of the systems in real-world conditions under some time-varying behavior, uncertainties due to varying over time, environmental changes, measurement errors, etc. And so, yes, so it's an important thing to say. We trained our model with 6 terms of in the orthogonal expansion, because this number actually gives us the best trade-off between network complexity and accuracy. After the model has been trained, we embedded it into our controller, and we validated the performance of our controller by comparing it with 2 other control strategies, which have already proven to be suitable for the control of TRAS. The first controller was orthogonal endocrine intelligent controller, OEIC. And the second controller is classical MPC controller designed with linearized model of TRAS. So on this slide, azimuth angle and pitch angle are figures of azimuth angle and pitch angle are presented, and we can actually see that all these controllers can fulfill their purpose in tracking the desired trajectory. But in order to see the real difference between their accuracy, we calculated the root mean squared error. So from this table, we can see that the newly proposed algorithm has much better accuracy than classical MPC, but still its accuracy is not as still a bit worse than accuracy of orthogonal endocrine intelligent controller. But it has shorter training time. And on the other hand, this orthogonal endocrine intelligent controller achieves the best accuracy with great controller complexity and cost. The real strength of our new controller can be noticed if we actually introduce disturbances into original nominal system in order to imitate some environmental changes, uncertainties, or measurement errors. So we also performed 2 more sets of experiments. We introduced change in nominal system response with noise to signal ratio of 1% and 3%. And the results are shown in this table 3. We can see that actually orthogonal endocrine intelligent controller and classical MPC cannot adjust well to these changes, and they require new training in case of OEIC, or finding new state space matrices in case of classical MPC. So and we can see that their root mean squared error significantly increases. On the other hand, the newly proposed control algorithm has incorporated directly incorporated measure of variations, the delta factor, into its AOPN model. And this controller does not need to be trained again. The only modification which has to be implemented is just perturbating the value of delta a bit. The model was the original model was trained with the delta set to 1, and here we only we changed it to 1.01 and 1.03 for changes of 1 and 3% respectively. And we can see that the controller actually keeps its tracking accuracy. So to conclude, the newly proposed controller demonstrated satisfactory performances in conducted experiments, in pair with much more complex and expensive orthogonal endocrine intelligent controller, and it has much better accuracy than classical MPC. I would also state that I would emphasize that superiority of the novel controller actually becomes even more obvious when we introduce disturbances into original nominal systems to imitate environmental changes and measurement errors. And that's all thanks to the built-in adaptability of AOPN model. So that would be it. Thank you for your attention. I hope I didn't take too much. It didn't take too much time.
No, thank you. Thank you for a very well presented presentation. So please, questions from the audience. Okay, then I will ask you something. First, my first question is, which training algorithm did you use to train orthogonal polynomial network?
We used Levenberg.
Marko, yes. Did you test also some other different algorithms?
No, we did it this way now. This time we did it this way, so yeah. Okay,
and did you maybe tested probably other neural networks like radial basis neural network models? Because this is similar, like polynomial
no, we
networks.
compared it with this orthogonal endocrine intelligent controller. It was actually developed by Professor Miroslav Milovanovic. He is also author of this paper. And we compared it to that system. It's actually a hybrid controller, and it consists of orthogonal endocrine neural network and adaptive neurofuzzy inference system. So yes, it's a complex structure. So we compared it to that model.
Okay, thank you very much for your presentations and answers. Now we will continue with the fifth paper. In the fifth paper, we have next paper is with the title Binary Quantization Analysis of Neural Networks Weights on the MNIST dataset. This paper will be presented by Mr. Nikola Vucic, and Mr. Nikola Vucic, I give you a floor to presentation. Is Mr. Nikola Vucic not here? Is maybe some other author here?
Previously he was.
Yes, previously he was. Maybe.
If he is not here, we can do our presentation if you like.
Okay. Then we will continue with the last presentation, and later we will ask if Mr. Nikola is here. And okay. Okay. Then next presentation is implementation of PID type sliding mode controller design based on fractional order calculus for industrial process system.
Yeah.
So,
hi.
Mr. Kagan, you can start.
Hi, everyone. First of all, I would like to thank you to Professor Darius because our presentation was yesterday. The time is yesterday, and he shifted today for us. Thank you very much, Professor Darius, for this. And our presentation is implementation a PID type sliding mode controller design based on fractional order calculus for industrial process system. And we are given this presentation from Turkey Erzurum Technical University. And this presentation is about coupled tank system. And this, just a second. Yeah, and in many industrial areas, the liquid level control between tanks are crucial applications such as water distribution, biochemical power generation, petrochemical processing. In these applications, the liquid is stored in more than one tanks, which connected together with the hull. In this type of system, generally, we can say that electrical pumps are used as actuators to motorize valve system. For example, in addition to this, we can say that flow meter and pressure sensor can assist to obtain liquid level for the purpose of control application. These process systems has nonlinear behavior due to their we can say dynamic parameter variation and pump valve characteristics. Classical industrial process application in industry, traditional PID control methods are a beneficial controller method for linear and basic system. In spite of this, the classical PID type controller methods are incapable to fulfill the demands of controlling high accurate liquid level during the application due to the nonlinear behavior of the system, we can say that. For this purpose, many nonlinear control algorithms have been performed to control this type of system in industry. To solve the problems mentioned above and to provide high precision liquid level control, a nonlinear control method should be used during kind of these real-time application. In the literature, various nonlinear control techniques are performed to liquid level process system to obtain high precise control, such as we can say like adaptive base and fractional order controller, backstepping controller, we can say it is used in industry as well, and model-based backstepping controller and sliding mode controller and so on. Sliding mode controller methods have gained attraction recently, especially as a process control algorithm in industry. We can say that definitely. The crucial benefit of sliding mode controller is an effective and robust control process in terms of the unknown parameters and unmodeled dynamics. In addition to this, by controlling a nonlinear, sorry about that. What I say, in addition to this, by controlling a nonlinear dynamic system in terms of the external disturbances of uncertainties, system states have stayed on the sliding surface with the help of the switching function in sliding mode control. Fractional order control technique is also a very attractive control methods in the literature recently in terms of increasing the efficiency of the above mentioned, or we can say aforementioned controller techniques. In some studies in the literature, fractional order is considered during the process control to increase this system robustness due to an arbitrary order of the ordinary and the integral calculus. What we have done in this work, a mathematical controller design has been developed for considering the benefits of fractional order calculus and sliding mode control techniques. Design fractional order with PID type sliding mode control technique has been performed for controlling the proposed liquid level control system. The reason of performing fractional order calculus combination with we can say PID type sliding mode control is to provide fast finite time convergence and accurate liquid level tracking, we can say that, and chattering free control. And also we would like to avoid uncertainty during the real-time process motion. Moreover, a nonlinear dynamic equation of the liquid level coupled trunk process system have been analytically obtained in this work. We can say, like, I would like to show the effectiveness of the fractional order PID type sliding mode controller. Experimental application is executed by the conventional feed-forward PI controller technique. Real-time execution and outputs prove that the given fractional order PID sliding mode controller technique progressively increase the system controller efficiency when we compare to the traditional process control techniques. The liquid level coupled tank system is illustrated in this figure, as you can see, right corner. An electrical motor actuates the system pump. As shown in figure, tank 1 and tank 2 are connected together with an orifice. Additionally, each tank has the pressure sensor for level measurements. As you can see from the table, our coupled tank system parameters are given in here. This is the tank parameters. And using the fluid dynamics and Bernoulli's law can be obtained mathematical model of system in Laplace domain, as you can see here, this equation G1 and G2. The detailed mathematical model of the system can be found in detail in our paper. Summary, G1 is the transfer function of tank 1 here, and this function input of the system is pump voltage and output state is level of tank 1, and also G2 here is the transfer function of tank 2. In this function, input state is level of tank 1, output state is level of tank 2. In this case, the state variables of the system can be defined as here x2 and x4, and their derivation will be x1 and x3 dots. Sorry about that. By taking the inverse Laplace transformation of the transfer function, and second order differential equation of the system can be obtained as x1 2 dot and x3 3 dot in this equation. The process outputs are given by, this is here, time to x2 and time to x4, and time to u21 is the equal to control input of tank 1 is equal to Laplace time to u22 is equal to L1 are the control inputs of the tank 2. Hence, the second order equation of motion can be obtained in a matrix form as X here, X2 dot, you can see from here, where the bounded lambda uncertainty is given by at the end of the X2 dot equation. This model will be used in our proposed fractional order sliding mode control technique. And in this study, fractional order PID type sliding surface function, which is time to S, is created by using fractional order calculus as follows in this equation. And in this equation, Kp, as you can see here, and sorry about that, Kp and Kd and Ki are the control gain parameters in this equation, and Et is the tracking error function in tanks. After all many mathematical calculation, the total feedback control law can be obtained in U total, as you can see here. And in order to obtain this equation, there are many steps to calculate. This control equation consists of, we can say that consists of two control parts. The first part is equivalent control load. The other part is switching control part, especially the signal function as shown in U total, as you can see here at the end of the signal function. And U total equation demonstrates S a part of switching control law. And in this experimental application, the proposed control approaches has been verified by performing experimental tests on a real couple tank system using the control block diagram as shown in figure. What we use this experimental application, we use MATLAB Simulink toolbox, and also we use the real-time Quasar data acquisition card for real-time application. And to test the controller efficiency, a step and the sawtooth reference signal are combined, and as you can see, used together on both tank configurations for tank 1 and tank 2. In this figure, show the liquid level trajectory tracking of the proposed fractional order PID type sliding mode controller. As seen from the figures, the proposed fractional order PID type sliding mode controller provides a pretty fast and effective outputs during the real-time execution. And in addition to this, performing an acceptable small overshoot on the trajectory and precise tracking performance as compared with the classical PI controller. And also we did this stability analysis for this real-time application, but there was a limited page for the conference. That's why our referee said to us, could you please take it off some parts of the paper? And we just took it off almost, I think, 2 pages from our paper. And also why we did to compare the PID type sliding mode controller with SEMEJ, we can compare with the sliding mode controller. We could do that, but in industry, many these applications will be it controls with PID controller. That's why we would like to compare it with PID type controller. That's why in this figures you can see the comparison between fractional order PID type controller and feed-forward PI controller. This is my conclusion. What we have done in this study, the proposed fractional order PID type sliding mode controller method has been presented and validated on a couple tank system to show its strong robustness and precision. To achieve finite time convergence and better tracking trajectory, the fractional calculus has combined with the sliding mode controller. And a well-tuned classical sliding mode controller is also performed to tank system to show the superiority of the proposed controller. The experimental result clearly showed that the proposed fractional order sliding controller method has performed effectively in perspective of rapid response, fast finite time convergence, and significant improvements in terms of minimizing the trajectory tracking error when it compared to the response of the classical PI controller. And this is my presentation, and thank you very much for
Thank you very much for your presentation. Maybe any questions from the audience?
I can hear. Sorry.
Sorry. Now do you hear me?
Okay.
Yes, thank you for your presentation.
Thank you.
Do you have any questions maybe from audience? Anybody of you of presented person? No, there is no questions. Maybe in chat also. In chat, I don't see any questions. Okay, then maybe my question is, how will you continue your research? What is next? What is interesting for you? How to implement this new algorithm? Where you can implement it?
Okay.
Do you have any project or something like this?
Yeah, that's fine. Can you hear me?
Yes.
Okay, isn't it? Okay, that's fine. What we're gonna do next, now, to be honest, we are preparing a next paper, and it will be like adaptive future in this algorithm, it will be. And then we would like to compare this adaptive algorithm with like integral sliding type controller, and also like, or we can combine with fractional order calculus with integral type sliding mode controller, and we can compare with the adaptive type sliding mode controller in this paper, future work, like a future work.
Okay, thank you very much for answering presentation. And now we will continue with our last paper. I think Mr. Nikola Vucic is now present.
Yes.
So I will repeat the paper is the binary quantization analysis of neural networks weights on MNIST dataset. Please, Mr. Vucic, you can start with your presentation.
Hello, everybody. My name is Nikola Vucic. I come from the Faculty of Electronic Engineering of the University of Niš, and it will be my pleasure to present you our article, The Binary Quantization Analysis of a Neural Network's Weights on MNIST Dataset. We are done, the team led by Professor Zoran Peric, and the other authors are Baoyan Denic, Milan Savic, me, and my colleague Nikola Simic. So I will shortly introduce you to this topic. Neural networks, or NN, have become popular solutions for different challenges due to the increasing availability of powerful hardware, but neural networks have very complex architectures. So they have a large amount of parameters, computational and storage resources. So that can be a limiting factor for their application in portable and edge computing devices with limited memory and processing power. Therefore, there is a need for NN compression and quantization, and quantization is widely used for that purpose. Neural network parameters, their weights, activations, etc., usually represented in 32-bit floating point format. That's actually the full precision format, are mapped to fixed point representations using lower bit lengths. So we notice that Laplacian distribution can describe well the weights of neural networks as well as the speech, so we will make a parallel in this article. Further, we derive closed form expressions for performance estimation and introduce two criteria for the selection of the quantizer for the variance range of interest. Theoretical results are further verified on real data using the weights of neural networks observed for the handwritten digit classification problem. So we have both theoretical and experimental approach in this paper. And finally, the influence of binarized weights on prediction accuracy is also investigated, and the relation between the weight quality measured by SQNR and accuracy is established. So first, we started with the design of binary quantizer for the reference variance. It is the symmetrical binary scalar quantizer presented for two levels, and its input data source is described by the Laplacian probability density function, and the quality of the signal is measured by signal to quantization noise ratio, and you have the formula here on the bottom right side. When we draw a graph, you can see it here, and we also looked for the maximal data limit. This is X max optimal, and you can see both here on the graph, and it is also mathematically derived that optimal value is square of 2. Then we further examined our investigation. So here we consider the situation when a binary quantizer designed for the particular variance, it's actually for one variance, is applied on the Laplacian inputs having a variance different from the designed one. It is variance mismatched quantization. So variance mismatch effect reduces the efficiency of the quantization model over the broad variance range. So robust quantization models are recommended for non-stationary data processing, as they can satisfy minimal quality requirements over the entire range. So here we will analyze the binary quantizer in a wide dynamic range and derive expressions for performance evaluation. So first, in the previous slide, we had the single variance value, and here we have the broader range, and we examine the parameters within this range. So in addition, criteria for selection of a binary quantizer in the established variance range of interest will be proposed. So we will have two criteria, and we will see how to choose the best quantizer. So design of binary scalar quantizer for a wide dynamic range have these performances. This is the distortion. Depending on the variance, you have here the formula, and the SQNR is given by the following formula. So when we plot the graphs for different X max values here from 1/2 to 4, we have 5 lines. And we also looked for the maximal value of SQNR, and it is specified at this point, X max of sigma divided by the square of 2. So it is also visible on the graph that this is the maximal value just in the logarithmic scale. Further, we also plotted the distortion as well, and the distortion achieves the minimum in the following point, X max divided by 2 and the square of 2. So these optimal values for the SQNR and for the distortion are not the same. So in this table, we have shown the values for the optimal values of sigma, the variance, for maximal SQNR and for the minimal distortion. And it can be observed that the sigma for the maximal SQNR is 2 times larger than the sigma for the minimal distortion. And then we introduced two criteria for a selection of the binary quantizer. So the best quantizer from the set of quantizers, the one with different X max, needs to be selected for the particular variance in the defined variance range, observing SQNR as a performance criterion. So the following two criteria proposed. The first criterion is the selection of the quantizer with the maximal average SQNR achieved in a defined fixed variance range. So we calculate an arithmetic mean of the SQNR, and we choose the one with the highest value. So it's very simple solution and very simple approach. And the second quantizer is different. It considers robustness as well. It has, besides taking account SQNR average, the best quantizer has to fulfill one additional condition in the given range, and that's the condition that the SQNR is above the limit equal to 1 decibel. So, for example, here, we take a line equal to 1 decibel and find the lower and the upper limit of that border. So we give the table according to the second criterion. For example, it is also visible in the previously shown graph with 5 lines, the lower and the upper limit of these ranges, and they're given here for different data limits here, and also as well as in the logarithmic scale on the right. We can notice that these ranges are approximately 7.6 decibels wide. So in the following 2 tables, we will show the SQNR average of the binary quantizer with different X max for 3 arbitrary selected variance ranges and the width of the interval where the second criterion is fulfilled. So here we have different ranges and we have chosen the 3 arbitrary ranges. They are the following: from -3 to 15 decibels. The second is from 0 to 18 decibels, and the third is from 5 to 25 decibels. So the upper table is for the first criterion. So here we choose the quantizer with X max equal to 2, and here the X max equal to 4. And this is the so here these are the average values of SQNR, and the second table is the table the width for the second criterion, and we can observe here that the same quantizers are chosen for the both tables. So both criteria give the same solutions. So we have further continued our research with experimental results. So we wanted to verify our results with experiments. So our experiment is focused on the feed-forward neural network named the multi-layer perceptron, or MLP, a classical network with input, hidden, and output layers. So we use MNIST database as input, having 60,000 monochrome images of handwritten single digits of dimensions 28 × 28 pixels, where for training and testing purposes, 50,000 and 10,000 images respectively are used. So the number of nodes in the input, hidden, and output layer is respectively 784, 128, and 10, which is also the number of classes because we have digits from 0 to 9. So the rectified linear unit ReLU and softmax activation functions are used in the hidden and output layer respectively. So the regularization rate, learning rate, number of iterations per epoch, and batch size are set to the following values. And the MLP neural network is trained for 20 epochs, achieving the prediction accuracy score of 96.7%. So the histogram of the learned weights can be approximated with Laplacian PDF, providing the basis for implementation, the considered binary quantizer, or the post-training quantization. So this is the histogram of the learned weights, and we observed that it has also Laplacian PDF. So that's how we started our research from this observation. So we introduced the efficiency of quantizer on the real data, measured with the following function called SQNR-EX. It is defined in this way, and the correctness of the theoretical results in terms of SQNR is investigated on the range from 0 to 18 decibels. And the following table gives the SQNR-EX and prediction accuracy, or PA, for different weights sigma W. So here we have the table. Here are the weights in the left column, and these are the maximal data limits X max from 1/2 to 4. And here are the SQNR in this column, and these 5 columns are the prediction accuracies. It is also noticeable that prediction accuracy is the same even when the weights and the SQNR have the different values. So in this graph, we also plotted the data from the previous table. So on the left, we have SQNR-X, and in decibel, we have the weights here on the lower axis. So the selection of the best quantizer is based on experimental results. Will be done using the two previously proposed criteria. So we have calculated the values from this table. So we have the average SQNR-EX and the width of the interval where the SQNR-EX is higher than 1 decibel. So we have these values of the average SQNR-EX, and this is the width of the range where the performances are above 1 decibel. So we choose the underlined values as the best ones. So for the first criterion is X max equal to 4, and for the second criterion is X max equal to 2. So we will shortly discuss these experimental results. So quantizer designed for X max equal to 2 has been the theoretical choice for both previously described criteria. In this way, theoretical and experimental results have good matching. In addition, the weights quantized using a binary quantizer with various X max are then separately implemented to MLP for classification purposes on TASE data or 10,000 images from MNIST database, and the prediction accuracy examines. So this corresponds to the situation when the same non-adaptive binary quantizer is used for different MLP networks, as the set of weights is different in each case. So for a given binary quantizer defined with X max, each MLP achieves the same prediction accuracy score, although different SQNRs are provided. This is because the same quantized weights are obtained regardless the variance of the weights, and thus the quantized MLP is the same. Accordingly, in that case, the relationship between the SQNR and prediction accuracy cannot be uniquely defined. SQNR does not dominantly contribute to neural network performance. On the other hand, we can see that the accuracy of the quantized MLP increases as the binary quantizer uses higher values of X max. So as previously described, the highest performance of the quantized MLP is achieved when the quantizer is designed for X max equal to 4, and then the prediction accuracy is 92.24%, and slightly lower when the quantizer with X max equal to 2 is applied. Then the prediction accuracy is 91.93%. Note that these two quantizers are already proposed as the most appropriate based on SQNR analysis performed above. Further increasing of the parameter X max. So when we look for the X max larger than 4, will result in negligible increasing of MLP performance. Finally, one can notice that MLP with binarized weights provides a lower accuracy score for 4.46% or 4.84% for these two values than that achieved with full precision weights, at the same time reducing the network size by factor 32. So to conclude this paper and the presentation, we should say that the detailed analysis of binary scalar quantization of Laplacian source has been carried out, along with an application for compression of NN parameters. Closed form expression in terms of SQNR and distortion have been derived for analysis in a wide dynamic range, and two criteria have been proposed to select the best quantizer. Verification of the theoretical results in terms of SQNR achieved in a wide dynamic range and quantizer selection has been done on real data using neural network weights. Furthermore, the selected fixed non-adaptive binary quantizer has been applied to compress different MLP networks with the goal to establish a relationship among the SQNR and prediction accuracy. It has been shown that each quantized MLP is the same regardless of the weight variance, although for different weights, different SQNRs have been observed. Therefore, the uniquely defined relationship has not been established as SQNR does not dominantly contribute to neural network performance. In addition, the relatively high prediction accuracy has been reported, over 92%, that is only 4.46 lower than the full precision model, along with the compression gain of 32 times. So it was my short presentation of our paper, and it is expected that this article will be published soon in Electronica Electrotechnical Journal. So I am kindly inviting you to read our article and maybe to send us some question later. And that was my short presentation. Thank you for your patience.
Thank you, Mr. Vucic, for your nice presentation. Maybe one short question from the audience. There is no. Yes. Okay. Mr. Vucic, just one short question. This is very nice analysis of the usefulness of the binary quantization or binary quantizer. Can you briefly tell us to which practical neural network applications would you recommend it to use of the binary quantizer technology? For which applications you propose it is good to use it?
We will use it probably in some voice recognition and emotional recognition neural networks.
Mm-hmm. What about probably time series analysis and so on?
Well,
or prediction
we haven't
models.
considered that approach yet, but it is interesting to hear it.
Okay, thank you very much for your answer. Now we are on the end of this section. I think my opinion is that all 6 presentations were very interesting for all of us. I congratulate all presenters for their presentations. I hope that we will meet us somewhere in the real world, not only on the Zoom. Yes, and okay, have a nice day. And I will give now a word to the chair of the conference, to Darius.
Marjan,
Darius, will you say something?
Yes, maybe some information.
Yes.
Thank you, Marjan, for chairing, for very good chairing, and thank you, presenters, as well. And I would like to invite you to join after 40 minutes to the closing session. It will be some official information and best paper award. And yes, don't forget to vote for the best paper. Okay, so we still have 40 minutes. So as soon as you can manage, I would be glad, because I still have to collect all information. Okay, so thank you and see you after, I hope, 40 minutes.
Okay, thank you.